Oh, okay. Thank you all for sitting and not leaving the room when I came in. That's good. I should mention that much of the work you see here is from our team. We have many graduate students and research scientists that have been involved in many of the things that you'll see here. Anything you see good about it, attribute to my students and my staff, and then anything that you see that's terrible, the buck stops here. Okay. I won't go into too much detail of the theory of surface renewal, but I will try and cover all the different methods that can be used for evapotranspiration, and there are many that can be used to estimate this. You heard some of them already today, I believe, earlier this morning. So the main sort of scientific basis, besides any of these, engineering and scientific basis, is mass balance and energy balance. Closer? Okay. And the scales that many of you are interested in can range all the way from individual plants that might look a little sick or something, and you want to know about that individual section of plants, or even an individual plant, or leaf even, all the way to regional scales. I was just telling one of your audience members a bit earlier how we did some estimates for all of Europe. So it can go from regions to global scales down to leaf and field scales. Some of the equipment you see here are things that are developed for measuring this at a field scale that you'll see here. And here's an example of what field scale measurements have to go through. They have to go through rain, dew, condensation, birds, animals that might be grazing that knock down your equipment. All sorts of things can happen. And of course, everything has to be done in agreement with the growers or farmers that are in the area. How many of you can see pictures that show birds, for example, influencing measurements here? Which of those pictures? How many pictures do you see that you think have birds in it? There's at least one, actually two there. If you look carefully, it turns out there are two that have birds in them. So these are things that are not so nice. Suppose you have net radiometers or equipment. Birds are not well trained to go to the litter box like cats might be, for example. They're sort of more like dogs that, they'll go almost anywhere and they do it when they want. And so they do it on your equipment a lot of times. Your equipment looks like a nice bird condo to them half the time. So you have to be careful, and anytime you have field equipment, it means you have to be out there trying to take care of your equipment and making sure it's not too messed up by things like bird poop. The methods I'm showing can be used for large scales too. This is an old-growth forest that's around 60 meters tall. That equipment you see there is trying to measure evapotranspiration at about 70 meters up. So this is over 200 feet up above this old-growth forest. So to deal with stuff that's out there with birds on it, you have to bring the equipment back into where you can deal with it on a tower that's very tall. You have to be essentially something called a tower dog. You climb up these towers and you deal with your equipment and you put them down. It's so a little scary being up that high because if you fall down, that's it, usually. Okay, so I'm going to go to some things that you saw earlier this morning. I believe there were some soil balance type methods that were shown to you. So this is an attempt from an atmospheric scientist to show you something about this soil balance, which is you have all these terms coming in on the surface, below, going down horizontally, going down vertically, going across horizontally, I should say, and evapotranspiration. So if you're trying to get evapotranspiration, for example, from taking things like soil measurements and flow measurements, you might have something that looks like this, where you look at the inflow and outflow on the surface, inflow, outflow in the soil, and the inflow and outflow in the soil can be both horizontal and vertical. Okay? And then the residual from all that would be the evapotranspiration. That's the other term that's there. Does that make sense to everyone? So some of you take these soil measurements. I'm an atmospheric scientist. I only took 2 hydrology courses a long, long, long time ago before many of you were born. So tell me if I'm missing anything here. I might be. Anything, does that look about reasonable to everyone? Okay, so this is a mass budget, right? It's a concept of conservation of mass. We're assuming we're not going close to the speed of light. We don't have to deal with relativistic issues that might change mass and stuff like that into energy. So we're in good shape here. So if you're trying to use soil sensors, what are some of the challenges? you go around and you look at your soils, you take soil maps and things, you realize there's a lot of heterogeneity that occurs, right? You've seen that. I've done a lot of work in the Delta region recently, and the soil maps of some of those islands in the Delta are just amazing. You see all this variation in a single island when we're trying to think it's the same. Well, that makes an implication that when you're taking your soil measurements, they're usually just the local region, almost like a point around where your sensor is, and sometimes a little more distance depending on what type of sensor you're using, but still pretty close to not the whole field. So then you have to put lots of soil sensors out if you want to really characterize the whole field, unless you have a very homogeneous soil, which is possible in some areas. So that's part of the issue that could be a little bit challenging when you take the soil measurements. Another way, besides looking at individual fields, we now have satellites, the SMAP type of satellites that look at microwave type of signals that come from the soil. They only go down a few centimeters. But NASA does put out something that goes down deeper, and that's because they use a model to then say what happens when you've got that surface stuff to get satellite type data. I think Susan Houston and some other people might be talking about other remote sensing methods later in this workshop. There's also something called GRACE, which is nothing religious in this particular case. It's looking at gravitational anomalies from satellites passing over, and they use that to try and figure out how much water change could be occurring. That's integrated all the way down, though, because it's looking at gravitation. So it's all the way down. Includes groundwater, includes anything that could be occurring. So that's another type of satellite method that could be used. There's some horizontal resolution problems with some of this remote sensing. You can't look at field levels as easily in many cases. Another mass balance that sort of does soil type of issue is to use a lysometer. How many of you have actually used lysometers or seen them here? Yeah, Larry, of course, you've seen them. Here's an example of what used to be, and I think it still is. It, for a while, was eclipsed by a different lysometer around the world, but I think now we're still the largest lysometer right now in terms of actual volume. We have 20 feet in diameter and 3 feet depth, and we have 2 of these at UC Davis at the Campbell track. There's a picture of one sort of on the middle lower right. There's a cross-section of one. There's a picture there of what it looks like. And what you've done in terms of mass balance with a lysometer, you cross out all those other outflow things because it's like a big pool filled with soil and the plants. So you're only measuring what's going out, the ET, and what comes in from the top, rain. It didn't put down precipitation or snow. Okay, so that's a lysometer. That's one way you can measure things. You just measure the weight usually. Sometimes you can use other methods to measure what's going on in the lysometer, including nutrient stuff. You saw Christina mentioning things about nutrients, for example. You could look at nutrients and things like that also. So, if anyone wants all the coins in this wallet, tell me what commodity or species is on the lysometer in that picture or that actual photograph. If you can guess what that actual commodity is or identify it, the species, please. I will give you all the coins that are in here. There are only a few. Anyone want to hazard a guess of that commodity? Huh? Cannabis. Very close. It does begin with a C and end with an S. There's canvas on pieces of wood. I don't know the species of the wood. That one of my grad students was using to calibrate the lysometer, spraying these artificial plants that were sort of made out of dead plants, right? And then looking at the dry down from here. Okay? And also, he was trying to look at, as you look at that, see the bare field surrounding it? He was looking also at the so-called clothesline effect of lysometers that can occur. If the lysometer looks a lot different than the surroundings, how accurately does it measure what's actually happening in the lysometer because the surroundings might be different? So that was one thing going there. So I guess I get to keep my 12 cents of whatever is in here. It was a good guess, though, in some ways. Began with a C and ended with an S. Okay, so other mass balances that you might have seen or heard of or used even, things like pyrometers or leaf chambers or plant chambers that are put over the plants. Again, these are really small scale, though, right? You're only seeing a few leaves or a few plants when you do that. They also frequently they take a person to be out there taking the measurements. You have to be out there. So unless you have cheap graduate students or cheap labor, undergraduate interns, stuff like that, it's sort of difficult to do this on a long-term basis during the full growth of the plants, like Larry was showing a bit earlier, showing how things grow, the grapes going from the leaves being not very active to being very, very active and large. So you'd have to be sampling all that time. Okay, and sap flow was mentioned earlier today. So sap flow can also be used. Once again, there's an issue of scaling. You only can measure a few crops usually, a few individuals usually, and then you have to scale up. Doesn't always work depending on the type of plant, depending on who you listen to. Okay, so that's another mass budget. So how about going to the atmosphere? We've seen plants, we've seen the soil. How about the atmosphere? Everything has to be conserved, so any ET that goes from a plant or your grapevine that you have to then replenish by irrigation, for example, has to have gone in the atmosphere. So let's take atmospheric measurements. I'm going to start with the most complex one, actually, the eddy covariance or eddy flux measurement that you see here. It's looking at the measurements on the graph you see. That's humidity on the vertical axis and time on the horizontal axis. But that time is going a very small slot of time that I'm showing there. We take these measurements at 10 to 20 times a second. So your humidity has to be measured really fast to do this. And then we look at those turbulent fluctuations that are occurring in humidity. You look at also the wind speed. How much is that fluctuating? And when you look at the covariance, or how they correlate to each other, the variance of how they covary with the vertical motions and the humidity changes, you can get evapotranspiration. That's a mass budget method, it turns out. So it's a first principle method. However, these devices are relatively expensive. And the lower right-hand side, you can see how expensive these things are. You're talking about in the 20s to the 40s K. So 20,000 to 40,000. You could buy a Tesla 3 in the old price range from 10 years ago, 5 years ago, if you had made that little reservation. That was like 35K, I think, or something like that, right? So do you really want your ET, or do you want to be driving around in a nice electric Tesla showing off your stuff? I don't have any stocks in Tesla. So that gives you an idea that it's expensive, but you can do this, okay? And you do have to have people going out, chasing the birds away occasionally, or cleaning out your sensors that might have bird stuff on them, or be knocked over. One of the advantages or disadvantages is the large footprint. These things you put up at about 1 meter are measuring something from around 20 meters away to around 100 meters, and sort of like a diameter that's going there, or more ellipse that it's seeing, okay? That's the footprint of your measurement. So you're seeing a lot of your field. You don't have to worry as much about the heterogeneity, at least within that measurement scheme of a few hundred meters maybe. Sometimes tens of meters, depending on the conditions. So that can be an advantage to average that field. Okay? But you can have a disadvantage. Suppose you have a small field. Once when I was visiting Japan a few years ago, I saw these fields that were like inside the little triangles between some roads, and people were harvesting some stuff there. When you have this type of small field, eddy covariance is not that appropriate. Its footprint will be seeing whatever is upwind of the sensor, and it could be blacktop. It could be some other crop that you're not interested in. It might not be grapes. It might be almonds, something like that. So you might not be measuring what you think you're measuring if your footprint goes beyond your smaller field. So it's not that appropriate for really small fields, but it's great for large fields, if that makes sense. Besides being expensive, too. Okay, so another way that isn't used as often, there's some assumptions you have to make. You can reduce the cost quite a bit for small fields, is to measure upwind and downwind of that small field. What is the humidity coming into the field? What's the humidity leaving the field? If there's evapotranspiration, you've humidified the air. So it should be more humid. So if you measure the wind speed and you measure the humidity difference upstream and downstream of a small field, it'll work. We've used this for someone that Christina worked with, Will Haworth, to look at nitrous oxides, methane, and CO2 coming out of compost from decaying plant matter. we put stuff upstream and downstream to measure the differences of the concentrations of those gases, those trace gases. And guess what? We could get then an emission estimate for what's coming out from the compost. Not so perfect, right? You're thinking of things like landfill. Well, we'll do compost. Well, compost is not perfect either. They outgas also. And this would establish just how good they are compared to things like landfill. So that's an example, though. You can also use it for ET. You just look upstream, downstream. Small fields, really small fields. You have to hope that what's going above that box, you can see that sort of imaginary box, what's going upwards, though, is not being measured. So you have to hope that's small when you use a method like this. As opposed to the previous method, we're assuming almost everything's going up in terms of turbulence, and almost nothing's going in the horizontal in terms of the change of humidity. You're thinking it's well mixed. When you use this method, you're hoping that's not so well mixed, and things are just going from left to right in that diagram for a mass balance. Okay? But that is a method you can use for small, valuable things. If you're trying to look at the crop of some exotic guava tree, a set of trees that you have a little grove, and you want to know how much water is coming from that, you could try and use a method like this. Okay. So another method that can be used for large stuff is not used too much right now, but still can be used, is an aerodynamic method. It's cheaper than eddy covariance. You're measuring the vertical change, the vertical profiles of humidity difference that happen. And then you can use some turbulence theory to then estimate if you've got the wind speeds also at two different heights, and you've got the measurements of humidity at two different heights and temperature at two different heights, you could try and get essentially the evapotranspiration that way. It's cheaper, more inexpensive, but makes some assumptions that aren't made in eddy covariance. That you could get away with about maybe $5,000, or maybe a bit less even, depending what sensors you use. Okay? So another method that you might have heard, how many people have heard of Thule or have used Thule devices in their system? Well, Tom used to be in my lab. I know he officially had a different PI, but unofficially he was in my lab and developed his surface renewal, our surface renewal, a lot better during that time. That's using essentially energy balance linked to mass balance right now. We link it through the latent energy flux density. So here's a diagram of the energy balance of, say, a vineyard. You have net radiation driving everything, partitioned into ground heat flux and storage within the biomass of the vines. You have sensible heat, heating or cooling of the air, and then you have the latent energy associated with evapotranspiration. Okay? That all has to balance the net radiation. So this is an energy balance now, as opposed to a mass balance. But it's linked to the mass balance because the latent energy is linked to the evapotranspiration, and the evapotranspiration is part of the mass balance that we just saw earlier. The implication here is that we can rearrange this equation to solve for latent energy, which is essentially the evapotranspiration, by measuring or estimating the other three terms in that energy budget. Okay? So what are these terms? This is just to show you a general concept of radiation. It's just electromagnetic radiation coming from the sun mainly. But right now, do you realize that each of you is emitting up to about 400 watts per meter squared? And 400 watts because you're about a meter squared of area. Can you believe that? Well, this is an infrared thermometer that are used by some people to measure evapotranspiration. I will point it at you folks. Press this little button, and it's reading above absolute zero. So it means you're emitting radiation. And actually the value here shows you're emitting someplace around 400 watts per meter squared. So if you've seen the Addams Family, you might have heard of Uncle Festus, who can screw like light bulbs into his ear or his mouth and it lights up. You could light up 4 100-watt old incandescent bulbs, for example, or even maybe 40 compact fluorescent light bulbs. You put them in because you're emitting a lot of radiation, but it's also coming back to you. That's the long-wave radiation that comes from the Earth and from the greenhouse gases, including water vapor, in the atmosphere. So that's long-wave that you can't see, but you're emitting a fair amount. But short-wave radiation is the main thing that's driving it from the sun. Okay? That's the radiation term. Sensible heat is like the transfer of energy from surfaces to the air, and vice versa. And then conduction, G, the storage in the biomass and in the soil, is a conduction process, going in from hot to cold or cold to hot. Sorry, always hot to cold, I should say. Okay? And just to emphasize the latent energy, since that's a key part of this in this estimation for vineyards, it's the concept that there's a phase change going from a liquid to a gas inside your plant leaves or in the soil. When that happens, it takes energy. The latent energy represents that energy to change the phase from that liquid phase to the gaseous phase, where the molecules are bouncing all around and highly energetic. But when the liquid phase, they're a little sort of lazier almost. They're not bouncing and hitting each other, but they're still in the liquid phase, where there's a lot of the force fields of the water vapor molecules are now in a liquid form. And so it's not vapor and doesn't have that extra energy. So you have to add that energy to get to gas. Okay? So you need to break those hydrogen bonds, essentially, and the other intermolecular forces that are occurring in liquid to get to gas. The amount of energy is related directly to the evapotranspiration by the latent heat of evaporation. Okay? That's about 2.45 megajoules per kilogram. That's a lot. If you could boil a kilogram of water in a second, that'd be about 2.45 megawatts. A lot of energy. That'd be in a second. Luckily, that doesn't happen when we're cooking, right? You actually boil off everything and catch fires in your kitchen all the time. So it takes a lot of energy to do this. But that means if we have latent energy, we can divide by L, and we've got ET. So if you can measure the energy for evapotranspiration, you've got the mass change. Yay, we can do this. So how do we do this? Let's measure the net radiation. They're net radiometers. This is a bunch of different types from different manufacturers, so you don't think I'm just selling one type. Okay? You just put this over your field. You can measure that. Does it have to be over the field? Yes, if you're trying to measure stuff over the field. Don't put it over your head. That won't work. Don't put it over a tractor trail that's all compressed that you're using to access your vineyard. That won't give you the net radiation of all the vineyard. You need something representative, maybe at some height above it so you can see. Imagine it's almost like a fisheye lens that's on your camera. You can get fisheye lenses for your smartphones, right? Many of you have much smarter phones than my dumb smartphone that's here. You can put a fisheye on it. So these things are almost like fisheyes looking up and down. So they're seeing a wide area. So you want it to see your vineyard, for example. So you put it pretty high up and over a vineyard. You can measure it directly. Sensible heat flux. Here's the more challenging thing. You usually use some method to look at turbulence. You can look at things that measure eddy covariance, for example, that I mentioned earlier for turbulence. You can use the surface renewal method that the Thule system's based on that we developed at UC Davis. That's the concept of trying to look at those turbulent fluctuations just of temperature without the wind speed and be able to use that to try and figure out the sensible heat flux. You can use those aerodynamic methods I showed earlier, looking at gradients of temperature. Okay, so that's different ways, different expenses, all the way from tens of thousands of dollars to $1,000 or less. The surface renewal method uses thermocouples. Many of you, or several of you at least, are familiar with thermocouples. They're $10, $20, $100, depending on the type and fineness of the stuff you get. Pretty cheap. Then you have to log it, though, analyze the data. That's the more expensive part, up to $1,000 or $2,000. Thule charges you how many? How many people are paying Tom so that he can continue to support his family along with his spouse's income? How much are you paying? $1,200, $1,300 per year. Ooh, it's gone up. $1,500. And next year it'll be? No, just kidding. This is a good business model. He came to me when he was first trying to commercialize this and said, "Is it okay if I do this? You're a flaming liberal with, long hair and everything. Can I become commercial?" And I said, "Sure. It's your invention that you're doing here for this. What's your business model?" So he went and made a business model. That's the business model. You pay him a subscription, right? Does it automatically renew? No. Oh, okay. You can see he's very ethical about his subscription model. Not like Sirius. I have Sirius, and if you don't tell them, it just continues forever. If I die, my children will have to pay for it. Okay, So conduction, you can measure also the G, heat flux plates, temperature in the soil. What's the issue about this? That we've just discussed a bit earlier about putting sensors in soil. What's the problem? Spatial variability, the heterogeneity in the soil. So we can put it here, but suppose it's shaded. It's not going to be taking the same measurement as if you're in between your rows. Okay, so then you have to average over both shaded and not. So you can't just put one sensor down. You have to put several sensors down and average when you do that. Fortunately, G is not very large. So here's a diagram, for example, of net radiation, latent energy, sensible heat, and the ground heat flux for cotton. It just gives you a general idea of what's going on here. Sorry I didn't bring a vineyard example. But G is the one that's got the lowest amplitudes, that sort of bluish curve that you can see, that's close to the origin of 0. The vertical axis is the energy, watts per meter squared. Horizontal axis is the time of day. So you can sort of see that the G is generally a fairly small term in the energy budget. And over the day, look, it's positive, and then it's negative. Over the day, it averages close to 0. So if you're trying to do daily ET, you can average net radiation, average sensible heat, forget G, it's almost 0. You can get LE. Okay? So that's using the energy budget residual. You get LE as a residual of net radiation, G, and H, and if G is over a day, it's approximately 0. You just need to measure net radiation, sensible heat flux, by those methods we just mentioned earlier. Okay, surface renewal, eddy covariance, aerodynamic methods. Or, something I did mention a bit earlier, besides that, infrared thermometry. You can take something that's more expensive than that little device that I showed you that was measuring temperature, put it over your field, measure the surface temperature that's of your field, for example, and try and use that in contrast to the air temperature and with wind speed to try and get the sensible heat flux. And then from that, you can get that H term that's in that residual. You still have to get the net radiation. If it's over a day, you don't need G. Okay? Again, that's relatively inexpensive to do that. A few $1,000s. Those are just estimates, of course, right there. So you can see if you're paying someone every year a certain amount, over a certain amount of time, this initial investment may pay off, but you have to take care of it. Whereas when you're paying someone else, they're taking care of it. Okay? So that's a trade-off that you'd make economically over these things. Whether you want to sort of play with being a scientist, which is fun. I enjoy it. I'm sure many of you do too. I know scientific growing of stuff is a big thing. That is vineyards and stuff like that. Okay? And other ways to use satellites that you'll be seeing a bit later. I'll just briefly go into satellites here from a measurement viewpoint. Usually we always try and truth the satellite measurements with ground measurements to make sure everything's going okay. There's a lot of things that happen with satellite measurements. You're going through clouds, you're going through smoke plumes, aerosols, the air is not pure. All these things can vary your signal, the ways to try and correct for that. Susan is an expert in this, I am not, but she will talk about some of these things later. The general concept is you have all these things that can happen. If clouds are present, for example, you might not be able to use the remote sensing in the first place because it's not seeing your vineyard, it's seeing a cloud. Okay? It's all pretty common sense. The method that's used frequently, at least some of the satellite measurements, are using the same thing as those infrared thermometers that I just mentioned as one way. Try and get the surface temperature in some fashion, and then get the sensible heat from that. Use the energy budget residual, estimate the net radiation also from the satellite, for example, and then you can get latent energy. Okay? Very nice if you're trying to do a region, that's for sure. Right? If we're trying to do a region, we can't have thousands and thousands of these measurements. It's just very hard and expensive. It'd be fine for my grad students. And tell me ahead of time if you want all those measurements, because then I'll output a lot more grad students, and then they could help you with taking all these measurements. But it's really practical. It's not very practical to put out thousands and thousands and thousands of these measurements. So you have to use remote sensing for things like regional scale, the whole state, the whole country. When you're looking at that, it's just a necessity to do that. It's complex. Here's an example of one model, the metric model. San Luis Obispo is one of the heading areas for the metric model that's used. Pretty complex, lots of equations, lots of assumptions that go on to these equations based on measurements. There are lots of coefficients. Where do those coefficients come from? You don't just take them out of your head. They're coming out of measurements. So any errors in the measurements propagate into a model. I know I'm also a modeler, besides taking lots of field measurements. So the advantages are these large areas you can do. A lot of times they're less expensive for large areas, simply because you don't have to put thousands of stuff out. You can just use single satellite images. Some of the savings also, because satellites are not cheap. They're actually expensive, but you didn't have to pay for them except in your taxes that you went to sort of subsidize NASA and all these agencies that were originally developed to explore space and have the satellites go up. Disadvantages, every 8 days or so, if you're using 2 satellites, it could be a little sooner, a little more frequent, maybe every 4 days of using more than 2 satellites, but it passes over your field 1/70th of a second. Blink, you're actually several overpasses even if you blink. That's how fast that images of your individual field as it's zipping over. Then you have to figure out what's happening in the whole day, the weeks, and the months, or in between the passes. If it's every 4 days, for example, so you have 3 satellites in about every 4 days or something like that, you have to guess what's happening in between. Okay? The guess is scientific, so it's pretty good, but this is one of the trade-offs that you have. Here's an example of multiple models, including the one I just showed you, but other models too, of the Delta region of California here for 2016, just showing a color. Look, the colors look a little different in those patterns. It just shows you that the models, I'm just trying to show the models have variations because they make different assumptions. So the ET they put out is different because of the different assumptions they make. Okay? Here's another example of measurements on the horizontal axis measured in the field, and estimates from remote sensing on the vertical axis, taken in the same approximate period of something that was contracted by the Delta Watermaster. And you can see that's quite a bit of variation. The points are scattered quite a bit. Best fit lines are there for the different models, remote sensing models that were used. And you can see that it's different from the dashed line. That's the one-to-one. So this, again, just shows you variations between field measurements and remote sensing and between the remote sensing models themselves, that they have quite a bit of variation. So perhaps if you use them together and you sort of average them, you might get a fairly good estimate of the ET. But if you're using one individual model, you might have some variations compared to actual field measurements. The field measurements themselves also being imperfect. Finally, I want to introduce you to something else that we do quite a bit in my group, and that's using really detailed modeling, where you model all the way from the leaf and the root to the atmosphere. You look at radiation going into the canopy in 10 to 100 layers within the canopy. You look at leaves of different angles towards the sun. You have to look at the physiology. Are they opening and closing their stomates? How much CO2 are they taking in? That, in turn, relates to how much the stomates open, it turns out, with the models we're using. So when you look at that, you can divide up all those leaves into these classes of angles, whether shaded or in the sun, have roots, extract the water from the roots into the plant, and have it evaporate into the atmosphere using turbulent models, radiation models, plant physiology models. You can connect it actually to carbon-nitrogen cycling in the soil. We've done that also, where you put carbon-nitrogen cycling within the soil. That then implies how the photosynthesis and the health of the plant happens. We even have dynamic vegetation that sometimes can grow the plants from seed all the way to full grown, over hundreds of years for ecosystems, for example. So this all can be done. It can be done on your laptop. Models like this are, although complicated, laptops are complicated too. And so you can run it on your laptop. If you have to do a region, though, then you need a bigger system. But if you just want to do a field, you can do it on a laptop with a model like this, it turns out. When you attach it to regional scale models, such as WRF or the Weather Research and Forecasting model, then you need a larger scale system, although the advanced laptops can still run it for smaller regions. Not all of Europe or all of the US, but smaller regions, okay? The advantage of this is being able to link your carbon footprints, for example, to your water use, to figure out things like stress effects. You can put that all into a model like this. You have to have measurements initially to calibrate the coefficients that go in here. Grape photosynthesis for the different varieties is different between the varieties and between that and, say, that tall forest I showed you. They're all different. So you need to have that photosynthesis down in some way to figure out what's going on when you put it in a model like this. Garbage into a model, garbage out, right? Okay? So you have to have good input to get good output on this. But it does have this great thing of being process-based. You can figure out what's going on when you're doing different things, different treatments, different irrigation type of scheduling. You can try and figure it out with a model like this if you have enough data. I don't know if this has worked. Yeah, it does. This just gives you an idea of when you have the model output. This is over that tall forest that's about 65 meters tall. Horizontal axis is the latent heat, which is the evapotranspiration essentially, going all the way from the ground through the canopy to the atmosphere. So that stuff above is the atmospheric transport of evapotranspiration, and you can see how the canopy is putting out more and more evapotranspiration as you go higher and higher into the canopy as there's more leaf area there present. Okay? And you can use the simulation. This is an example of a simulation that's repeating. I call it a scientific meme type thing. It just keeps on going back and forth doing the same thing. But it's showing you how during the day you have a lot of evapotranspiration. During the night, guess what? You don't have much evapotranspiration. Sometimes even condensation or dew, depending on where you are. Okay? That's output from a model like this. Pretty cool. I won't show you the actual measurements that we use to compare. The measurements are much more jagged. There's more scattering in the measurements. So I'll skip that for a matter of time. And as I mentioned earlier, we can hook this up to a regional scale model, do all of California and some neighboring states even, to look at ET, evapotranspiration. So a publication from 2 years ago in agricultural and forest meteorology from one of my grad students, former grad students. He postdoc at MIT and now is back here in Davis. Shows, wow, you can look at ET not only at the field level, but scale it up to the whole state to figure out what's happening. So when someone tells you, you can't use this water, you're using too much water, you can say, wait, I'll look at this map, see where I am, and maybe I'm not using that much water. If I properly model it, properly measure it, I can show that. Okay, takeaway points. Field measurements can be relatively cheap or expensive for the field, for one field. As soon as you have multiple fields, okay, more expense. Technological advances could decrease these costs, as you saw with the Thule method. And then how many people use Wolf's device? Adam, Wolf's device? Yeah, the arable mark. How many people have that or have heard of it? So that's an alternative, for example, also to try and estimate things like ET and other things of your crop. So technological advances really miniaturize the stuff. You can even put them on drones now. So maybe that'll be the next thing. That's my dream for all of you growers that are out there. A drone that's automated once the FAA rules relax a little, where you don't even have to do anything. It just automatically jumps up, goes, surveys your field, comes back down to its little home base, recharges. Goes up, takes the measurements, comes back down. That'll be cool, and it's not that far away. Probably just 5 years or less, maybe. Things like that. Satellites or pseudo-satellites. These are ways to measure things remotely sensed above, quite a bit above, instead of a drone level. Those also might be improving. Pseudo-satellites, by the way, are these high-altitude solar-powered devices that fly and can fly for months on end and go over your sites. Okay? So that can improve things. Field measurements, they needed to always calibrate these other measurements. These other measurements are usually not direct. Field measurements can be more direct, and therefore you can always calibrate them. So you have to expend some money on that. Finally, we can use advanced models to look at what's happening on a very granular method, a very granular level, and scale that all the way to larger scales if you want, whatever scale you want. It is possible nowadays. My model I've shown here is not the only model. There are other models out there also. Okay? So I think that's about it. I just want to acknowledge all the money that went into this. There's a lot of money that's come indirectly from your taxes to some extent, if it's coming from federal or state agencies that have gone to do this research, and lots of people that have also been involved with this. So I think that's it. Thank you.
Any questions?
You're the plant, Daniele.
He's the plant.
Do you have any idea how, let's say, accurate or inaccurate would be taking, instead of having the site-specific measurement of net radiation, rely on something as a larger pixel size, like remote sensing, because we saw kind of quite a bit of discrepancy from our measurement on the ground with respect to Thule measurement in some situation, and in some other situation we didn't. So somehow I think it is related to where you are and what are you surrounded by. And I know it takes time to answer that question.
Oh, no, just looking to make sure I wasn't way over. I guess I talked really fast because I'm not way over. Yeah, so that's an excellent question. Thule, as far as I know from my spy who worked there for a while, and now the grad student that worked with Tom, uses a more estimation-based net radiation. For that amount that you're paying for it, they didn't want to have to maintain the net radiometers because birds sit on them and they they poop on them. They're sitting there, and this is the ideal roost for them, and they're just not potty trained. So, that's a problem. Most of you have heard of CIMUS, right? So CIMUS used to have net radiometers in the first year or two that they operated. Rick can tell you about that. He'll be talking later in this program. He can tell you that was the main cost, was maintaining the radiometers. So getting rid of that and using remote sensing methods, which is what Thule has done to estimate net radiation, is one solution to that. Are there errors? Yes. You always have increased uncertainty as soon as you have to infer something that could be directly measured with some other analog measurements, such as things like satellites going at some distance, or other methods that can be used. Sometimes air temperature along with shortwave radiation, which is easier to measure, not as inviting for the birds to sit on, can also be used. But yes, there's increased error when you use some of these methods that estimate net radiation rather than measuring. But even measuring net radiation, here's your sensor, right? You're trying to make it horizontal or sometimes tilted. If vineyards sometimes are in tilted fields, of course, and then there's controversy over how you mount the net radiometers over vineyards, for example, whether you're following the slope or whether you're doing it horizontal. Whichever you're doing, you're trying to get a particular angle. The angles you can get are only plus or minus maybe a half degree to a degree, practically, until a bird sits on it. And then maybe it's 5 degrees or 10 degrees even sometimes after that, and then you have to go running and change it and put it back. Okay? So there's errors even in the field measurements in net radiation because inherently you can't get more accurate than around maybe half a degree or so, and that creates errors right there. So even the field measurements have these errors, but the estimation errors are based on field measurements that then have made the estimate, and then you try and do some sort of regression analysis for that. So yeah, there's uncertainty when you do that, but sometimes it's necessary practically, unless you have someone going out to the field weekly or even more frequently sometimes, less frequently if you're trustworthy, if you have someone to scare off the birds, a scarecrow that's effective. They're not very effective usually, right? You have little cannons that blow noises to try and get them out. Or, drone system, you can have a drone that chases the birds away once it's automated. Yeah?
How is smoke affecting all of your data collection? I have Thule that didn't work with the smoke.
Excellent question. So whenever you use remote sense methods, things like smoke will confound those measurements and increase the uncertainty, increase the error. Okay? These measurements here actually tell you about the effect of the smoke. When it's ground-based, it'll reduce the shortwave radiation coming down, change it into more diffuse radiation than direct radiation that has a slightly different effect on canopy photosynthesis, for example. But you can see these things with actual measurements. So the field measurements aren't confounded by that. They actually tell you what the effects of the smoke are. And we see that happening. The only thing that can happen, though, if there's too much smoke, many of these fields are solar powered, right? Because most of you don't want huge lines of power going into the middle of your field to power up our measurements, right? You'd like us to be as unintrusive as possible. So we use solar power. If there's too much smoke, which happened in some of our Delta studies last year and several years ago, when there were smoke plumes that went over, we lost power, enough power that the batteries couldn't store enough, and then we couldn't power continually our measurements. So we have some days that are missing from the smoke. But it doesn't give you bad measurements. It just doesn't give you any measurements at all sometimes if you're solar powered with that smoke. But the field does help. Field actually takes that exactly into account. We're actually doing a study with one of the engineers in UC Davis right now to look at the eclipse even too, see what effects that had. No, not over vineyards though, over some grassland type stuff. Yeah.
So for all the methods that you described, how do you compensate for cover crop water use? So I want to irrigate my vines, not my cover crop.
Yes. So we have Daniele is looking into that in one of his studies that he's trying to involve our group with. That's more complex because now you're trying to measure evapotranspiration below and above. The model can do that. The model can do that. But to take the measurements to make sure the model's not lying to you in some fashion, or misrepresenting what's happening, you have to take some measurements. And these types of measurements, you can use some eddy covariance methods in just above the cover crop, but below the canopy. It is possible with some of the smaller devices, but you have to be very careful with them because you get too close to the ground, they have problems. The turbulence is weird enough that these measurements may be tainted as you get too close to the surface. So if you're maybe if you can deal with maybe a meter or so above that crop, that cover crop, then you should be okay in measuring that. The radiation also changes. So one of the things that Danielle and I have been talking about is putting radiation sensors to be looking at what happens with the cover crop compared to no cover crop, for example. That's an excellent question and definitely could have an effect. If you're using the soil measurements, soil moisture or soil temperature for the ground heat flux, you'll have to make sure you also properly sample where the cover crop is and where it might be less dense and stuff. But a fascinating problem.